Alright, so last time we got partway through a discussion of the structure of p-adic manifolds, and so we will just be continuing on with that discussion. So yes, I can find where we were. So next up, we do have a theorem to start things off. Going to let Q be the number of elements of the residue field of K. Now suppose our manifold X, our topological space, is compact, non-empty, and everywhere of the same dimension D, which is going to be at least 1. Then, first off, X is the disjoint union of finite balls. Secondly, the number of balls in such a decomposition of X is well determined mod Q minus 1. So X, which would make X determined up to isomorphism by an element of Z mod Q minus 1Z. Proof. Once again, we're just going to do a sketch mostly. One we've basically already seen. It's just kind of a restatement of what we've seen in a new context for number 2. However, we will need to reduce it. We're going to be reducing it, this second part down, based on the fact that you can divide a ball into Q to the eyeballs without disturbing congruences mod Q minus 1. So, first off, suppose X has decompositions into U sub I over an indexing set I and V sub j over an indexing set j. Where, of course, our indexing sets are finite and the our collections of that make up each decomposition are disjoint, not from each other, not from like U and V, but the various U's are disjoint and the various V's are disjoint. We want to show that the cardinality of I is congruent to the cardinality of of j modulo q minus 1. Okay, so first off, I don't know yet if we're going to prove these all afterwards or what, but first off we reduce to u collection of ui as a refinement of our collection of vi's. Step 2. We reduce to x being one such vj, and our indexing set for our v's just being j. So essentially we have one of them being just one ball. Then we have, in this reduced case, first off, x is a ball in k to the n. Secondly, each ui is a ball in k to the n. Thirdly, there exists analytic isomorphisms vi of ui into x such that x is the disjoint union of each vi acting on its respective ui. Next, you're going to want to reduce to each vi being a convergent power series. And then step 4, reduce down to each vi being Li composed with Ci, with Li a linear isomorphism, and Vi being an isomorphism from a ball onto a ball, which I'm going to call ball isomorphism. And then it says we can assume that Vi is Li. Step 5. We only need to show that there are radii Ri such that for Si the center equal to Ri, Li on Ui is the disjoint union of, I believe it's supposed to be balls of radius SI, and such that the number of such balls is a power of Q. If so, we can take R to be the minimum of our given radii, so X is decomposed in Q to the M balls of radius, what is happening? Radius R, and each LIUI is decomposed into Q to the MI balls of radius R. Then, first off, one is congruent to Q to the M. This is all mod Q minus 1. One is congruent to Q minus M, which is congruent to the sum over our i's of Q to the MI, which is congruent to the sum of just the number of elements in our indexing set, mod Q minus 1. So, thus from all this reduction, we need, we need to show if U is a ball and L a linear isomorphism, then there is a radius R such that if S is positive and less than R, LU is the disjoint union of balls of radius S, and the number of such balls is a power of Q. So, by translation and scaling, we can assume that U is the evaluation ring and that L is in the n by n matrices on this valuation ring of K, of course. Let M nu be the maximal ideal of A nu, and we note the number of cosets of, okay, they made a typo, M nu to the mu, with mu a positive integer, is equal to the number of elements in the evaluation ring mod this maximal ideal to the mu, which is q to the mu, with q the number of elements in the evaluation ring mod the maximal ideal. Okay, and then you have to give me 1 second here. We need this, we know this radius r we need is going to exist by a previous lemma. Yeah. We have such an r by previous lemma. And okay, I kind of missed notation, but such an r such that if s is less than r, I'll use the disjoint union of balls radius s. And we contend it meets the second half. Meets the second half. So we're going to take such an s between 0 and r. H be the number of balls of radius s in U. Then a nu to the n is the disjoint union of a finite number called h prime of translates. Translates is not a word people use. Translates of U. So the number of balls radius s in U times the number of translates is the number of balls of radius s in a nu to the n. Let mu be the positive integer such that is the ideal m nu to the mu is precisely the ball of radius s in our evaluation ring. Then our m nu to the mu to the n is the ball of radius s in the evaluation ring to the power of n about 0. So there are q to the mu to the n balls of radius s in a nu to the n Now, since we know though that our H prime is a power of Q, and we can note as H prime is the cardinality of A nu to the n over U, and since said A nu to the n over U is a torsion module over A nu, and hence a direct sum of modules of the form of our evaluation ring mod the maximal ideal to the power of some nu I, each of which has a cardinality equal to a power of Q. So H is going to be power of Q. Alright. And there's one last appendix note we're going to be going over before we get to our next chapter. Our next chapter is on analytic groups. So we're actually going to look at Lie groups next time. It's been a lot of setup here, but it's worth it, you know, to get yourself prepared for what's happening. Our last appendix note is on the transfinite p-adic line. And we know now that, we've seen firsthand that there exist non-paracompact Hausdorff manifolds over any locally compact ultrametric field K. And so here we're going to be giving an example which is stated to be by George Bergman. So we will construct a directed system, say x sub gamma of spaces indexed by the elements of the first uncountable ordinal and our example of a non-paracompact manifold will be the limit of the sequence of spaces. So, and I guess I should make a quick side note just in case you haven't seen it. There's this about like the transfinite numbers, the uncountable ordinal. I believe that's referring to like the first limit ordinal, right? Where you're essentially defining the natural numbers as being the collection of all smaller natural numbers. So 0 is the empty set, 1 is the set with 0 in it, 2 is a set of 0 and 1 in it, and so on. And then you have your first uncountable ordinal just being the set of all natural numbers with 0. And the idea is like you're comparing numbers by like, I mean there's an obvious way to compare numbers in that, so you can kind of treat it almost as a number in some context, but it's infinite, it's transfinite, quote unquote. So it's used a lot, and it's I've seen it before in classes as like an equivalent condition to like Zorn's lemma, axiom of choice, that fun stuff. Anyways, maybe I'm just rambling here. The manifolds X gamma will all be taken as copies of the evaluation ring, which here seems we're just writing as A of K. And we will define the maps sending a smaller manifold with a smaller index, that is, into a manifold with a larger index for delta less than gamma by induction on gamma. Okay, and once again, we don't have a base case gamma. A base case will be gamma equals 0, in which case there's no delta that's going to be less than 0, so we're done in that case. Yeah, I'll write it out just for fun. Base case 1, gamma being equal to 0, because we're using transfinite induction in this case. And there's no delta to satisfy this condition. Secondly, gamma is a successor ordinal, that is, gamma is equal to some gamma plus 1. In this case, let pi be a fixed generator of the maximal ideal m of x. And we're going to let the map from x gamma prime into x gamma be multiplication by this fixed generator, and then of course then we give arbitrary x delta to x gamma for delta less than gamma by composition. So you can define this directly recursively by sending x delta to x gamma prime, which we know is going to exist by induction hypothesis, and then by our current map to x gamma. But this is just going to unfold to like delta into delta plus 1 all the way up to gamma. And third, gamma is an initial ordinal. I'm guessing it's going to be non-zero in this context too. So this is our transfinite induction case. We're going to let y gamma be the limit for delta less than gamma of our x delta. So it's a limit of all smaller maps, all the smaller spaces. Then y gamma is the union of the countable family of open compact subspaces x delta for x delta less than gamma, and hence is paracompact. And so hence is the disjoint union of balls. With the number of balls being countable since a disjoint union must be locally finite and only, open a new page, only finitely many elements of a locally finite covering can meet any given x delta. Since our valuation ring without 0 is also the union of countable balls, we can choose an analytic isomorphism phi of gamma from y gamma to a minus 0. And then for delta less than gamma. The map from x delta to x gamma to orange gamma is defined as the composite x delta to our y gamma, then by this Vy to a minus a without 0, which is of course a subset of a, which we're going to be setting to be x gamma. And that gives us a definition for our function in the limit ordinal case. And this brings us to, I'm going to write it as a theorem. First off, any denumerable, which is a crazy word, denumerable family k to the n of compact subsets of x is contained in a compact set. And secondly, x itself is not compact. And proof of 1, since k to the n can be written as the union of each k to the n intersecting k gamma, x to the gamma, k gamma is not a thing. And our x gamma is open. There exists a gamma n with k to the n being inside x to the gamma n. Choosing a gamma such that gamma n is less than gamma for all n. We have that our k to the n lies within x gamma, and x gamma is compact. And part 2 is straightforward, just seeing that x gamma is not x for all gamma, which itself is an open cover, I believe, which is not going to be reducible. It does not have a finite subcover. And with that, we're a little under time, but that's the end of this section. I didn't technically show it's not paracompact, but that's left as an exercise. I will leave that to you as an exercise. Next time, we're finally done a review of differential topology. We can start talking about Lie groups now in a formal mathy sense, not just me hand waving a whole bunch. I do need to compare the two texts though. So that we might just double cover some of our stuff here, cover it twice. I feel like that's okay. Anyways, I'm done stalling here. Thanks for watching.